Programming, presented by
Guntram Berti.
Guntram, yeah, please.
Strange name. Здравствуйте. General programming, I think there could not be a better place to talk about general programming than Moscow, because, as all of you will know, Alexander Stepanov, one of the inventors of general programming, studied here in Moscow, and I think also developed the first ideas in that direction. So one could argue that generic programming was invented here, in a sense. So the subtitle is the good, the bad, and the, well, not the ugly, but the nice generalizations which make us move more upwards towards the Olymp of universal implementations. So, what is the march route for today? And you will imagine why I like this word, because I have never seen it, but I knew immediately what it meant. The first part of the talk is based on a talk I gave 1 year ago at the meeting C++ in Düsseldorf. It's a very gentle introduction to the concepts of general programming, using a very simple example, which is a sum, or more generally a reduce operation. But then we will find out there are some issues with that. It's not as general, not as efficient as we would like, and we would then go into the details and see how to fix these problems. Now, as a motivation, think about the following problem you might have at home. You want to drive in that screw. What do? You take a good tool, and your problem is solved. Very easy. Now, there is no one type of screw. There are several. If you look from above, it's even worse. So you need more tools. And this approach does obviously not scale very well. So the question is, can we do better in software? Or is software any different? So software is this incredibly flexible tool and should be somehow better, normally. But I have to disappoint you. So let's look at an implementation of a simple algorithm computing a sum of a vector of an array of doubles. Is that usable or reusable? In other contexts, it isn't really. If you change the type of the array to integer, you can't do it. Even if you pass a const pointer, it doesn't do it. So it's, in a way, it's ridiculous. It's a ridiculous implementation. It's completely overspecified. If you think it matches a single point in the huge space of possible applications of the sum, the mathematical sum. So it's really time to think about something more reusable here. Of course, sum is a trivial example or a very simple example, but you can easily think of more complex algorithms, more complex data structures than arrays and so on. And we will see in the end that even this simple algorithm has some ramifications which are not so simple anymore. So, well, the traditional approaches to reuse have been limited. If you use macros, object-oriented programming, all this doesn't quite cut it. I can't go into the detail today, but the approach which tries to attack that problem from the root is called generic programming. And what we really want is something like that. In the physical world, we have adapters for our screwdriver, and we want to have something which is equivalent in the software world, or perhaps even better than that. So what Alexander Stepanov said on that, we should try to separate the algorithms from the data structure as much as possible. As much as possible means not more than possible. That is, we want to maintain the efficiency of the non-generic solution. So this will be our criterion, and we will judge our solution against this criterion and see that we have some problems there. So the process is really to look at the non-generic implementation and see what are the restrictions with it, what are the artificial restrictions, and then try to remove that, and also to unify the access to data structures as far as possible. This is an approach which is also called lifting an implementation from a very concrete but low-level state to a more higher state, which is much more generic and can cover much more concrete situations. So Douglas Gregor I think he has coined that term, or is one of the people who have coined that term, says it's essentially what I just said. It's looking for the minimal requirements of the algorithms on the data structures, on the input data. So what are the assumptions of this piece of code we just have seen? Well, first assumption is, of course, we can only compute on doubles, not on floats, not on ints, not on any other type. Next thing is the values are in an array, not somewhere else. Have to be in a contiguous array so there are no gaps in the array. And now we will see how we can remove these restrictions and get a code which is more generic. So first one obviously is this type double. So this is easy one. So what do we do? Template, yeah, sure. This is easy, yeah? And we can do that in a minute. This was simple. Now we want to get rid of the array. This is perhaps a bit more difficult because the code as it stands is a bit, well, very tightly coupled to the array notation. So we must reformulate it first to see a chance to get rid of that. So first we get rid of that bracket notation here. That's not good. So we instead use star operator and then have to increment our v. And now, of course, we have to reformulate this one because we don't need the n anymore, actually. So what we can do is a different way to express how many items we have. And we can do that by replacing the n by perhaps another pointer, which is just v plus n. So something like that. This is an equivalent code. Just does it with different syntax. And now we look carefully about the functionality we actually need. And this is not that much anymore. So we have comparison here with another pointer. We have increment. And we have this dereference. Only these three operations we actually need to fulfill our needs to compute that sum. And that is much less than the full array functionality. And this can be supported by most data structures. And we create a new abstraction. I think you know it's an iterator. We have seen that. Generalization of a pointer to an array. With the pseudocode, just has to support these few operations. And, well, as I said, it can be supported by almost all data structures. Very easy. And here I have an example, a very basic, simply linked list rudimentary implementation. And we can define easily an iterator for this list. It's no big deal. I guess you have seen that before. OK. Just supports these and the operator and the comparison. And yeah, we can plug it in our code. So we have to replace the concrete type, still concrete type, the pointer type with the iterator type. Great. Then we have iterator, but now we have a problem. Yeah, what do we return? Our type t is gone. It's gone, and we have to somehow recover that. And there are several options. I can't go into all details now, but one option is just to pass it back as an extra parameter. So just pass it back as an extra parameter, and then we have an additional argument, which can be used as initializing argument. It would be 0 if we compute from scratch, but it could be an intermediate result as well. Now this has then we have full control over the type t, which is good in some cases because, for instance, imagine we have a sequence of floats. Then it makes sense to use double as a summation buffer because it's much more accurate. So it gives us much control. That's good. But the drawback is we have this extra parameter we always have to fill in if we use our sum, which is not good because we force the user to add something else. And also, which is a more subtle point, we don't always know the type t explicitly at the call side because we call it from within another generic function. It's not clear where we have perhaps the iterator but not the type t. It's not clear how we can spell out the type t here or get the init argument in a general case. So this will become more a problem if we further generalize sum to reduce where it's not clear where to start at all, at which value. So there would be another solution to somehow derive it directly from the iterator type. So this would be a map, a type map, which takes the iterator type and maps it to the value type we need. And the classic way to achieve it, which was also in old style C++ 98, is you define a template, a primary template, which tries to read the value which is embedded in your iterator type. Of course, this does work only if there is one. So for pointers, it doesn't work. There is no embedded type in pointers, so I have to do a partial specialization for that of that class. So you map for pointers, you just map it to the type pointed to. And for our list iterator, we just defined, we forgot that embedded type. We can have a full specialization of that template and just use int because we had int value types there. And now we can just use it. Looks a bit more complicated, but it works as well. Okay, these are the two basic approaches we can use. We will stick to the first one because it's more general and gives us more control, and we will use it in the sequel to derive more general versions of our algorithm. Okay, so it's also in the Iterator, in the standard library, it's called a bit different like that, but same procedure, same strategy. Okay, let's see if our sum is good enough. So let's say we have struct of employees and which have a salary field, and we just want to add all salaries to know what the company has to pay each month. So does it work? It doesn't. No, it doesn't. Now there is no plus on employee. And next thing is we want to have a vector of strings and we want to concatenate that. Well, it works kind of, but not the way maybe we would like. Yeah. And if we want to compute the maximum salary of all employees, well, we can't do this with sum. So let's think about what to do. It's not good enough. So this is a sum. And now let's see what we would have to do if we want to implement some of the other examples. Like start with the salary. We would have to replace it with that expression. For the string, we would perhaps like to add a space between the words. And for the maximum, yeah, we would have the maximum. Here, compute the maximum. And all these are very similar. They all have the form as equals operator of s plus star v. So it's very, very structurally similar because the rest of the code didn't change. So we just we just add this operator as an additional parameter. That's always solution. Problem, additional parameter. So we don't call it sum anymore. We call it reduce because it's normally called reduce. In the standard library, it's called accumulate. We pass the operator in here and then call op. All fine. And now our things work. And in C++ 11, it works even better because we can directly in place define our operators that we pass as a lambda function. Same for strings. We have something which adds that space, and yeah, we could even also define that for the maximum. So all good. Works fine, and we can even use that version to implement other functions of the standard library, like countIf. It just counts all items matching a predicate. And if we define an operator like that, like a struct counter, which just adds 1 to the counter if the predicate is true, otherwise 0, we can also implement countIf. So it's quite general. So it looks that we have matched the ultimate algorithm. Or do we? Not really. So there are a couple of problems where it doesn't really fully match our expectations. First thing is sequences where we don't know the end. Yeah, we'll look into that. Other thing is sequences which have some rich internal structure where we first don't know how to iterate over them, and if we do in a normal way, we perhaps don't get as a performance we expect. And third thing, the whole thing is sequential, and if we have a parallel machine, it's perhaps not that what we want. We want some parallel. But this is a different talk, not today. Sorry, time limits. Okay, sequences where we don't know the end of. Classical example is a C string. Yeah, so just we use a slight variation of our counting operator to count the number of the character E. The big question is, well, we know the beginning of the text, but we don't know the end. What do we put here? No ideas. I mean, one thing could be to call strlen and then just put text plus strlen, which would work, but of course, efficiency-wise, not the best approach because we go twice through the whole thing. That's not good. Maybe we can somehow make up an iterator value we can put here to achieve the right effect. This is something we'll look into. Well, I think what most people will do, just say, forget all this rubbish, this generic stuff, it doesn't cut it. We will roll our own count character. It's not so difficult. I make my own. Of course, we want to avoid it. We want to see how we can reduce our generic one. Or even we can have some more clever idea than these three here. So let's look at the first option. So that's a non-generic implementation. So basically, what we test really is just, the end condition is just a special value of the value pointed to. If we have a 0 character, we are at the end. And until we are not at the end, we just sum up. Well, the code is actually wrong because it doesn't test for equality here. So I must fix that. There should be a test, of course, for equality to see. But basically, the thing we are interested here is this test. So if we want to have achieve the same effect with a special value of end, we must trigger that comparison when we compare to that end value. And otherwise, we must just have the normal comparison of pointers, essentially, or iterators. So how can we achieve that? In order to trigger the second point, we must somehow recognize, of course, that we have a special value. So we must have a value which is distinct from all possible other values. And this is one possible implementation of an iterator or iterating over the strings. We have a normal, just a character pointer. And so either we have a default constructor which initializes that with a null pointer, which is our end, because it's not a valid state for any other string, or just initialize it with a valid pointer. That's the normal case. Okay, and if we want to implement our equality comparison, we must also have it must be symmetric in both arguments, and of course the end should compare equal to the end. And this leads to with complex code here. Yeah? We first test if one is 0, then the other should also be 0, or it should point to a 0 character, or the other way around. And this is the normal comparison. So it doesn't really simplify the things. But we can put it in our reduce. Here we have the end value, here we have the normal value, and it works. Good. All good? Yes. Yeah, it works. So it gives the right result. But now let's look at the code it is likely to generate. First, we look at the iterator category of this iterator. I didn't mention that, but random access iterator means we can jump arbitrarily from one iterator, add some value, let's say iterator plus 100. No problem. Can we do that here? No, because we can't do it for the AND value. Huh? We can do it for the others, but not for the AND. Same for bidirectional. We can't have a minus minus of the iterator because we can't do it for the AND. So we are more or less stuck with forward iterator. Yeah, not good. So not ideal, at least. And the other thing, if we look at the generated code. So this is a non-generic thing, which, as I said, has a bug. And the generic code would look like that here, which is first ugly, and second, likely not to be of the same performance, because we do a very complex test here, which we actually don't need, because we know, I mean, we have mapped this specific AND condition to a specific value of our iterator, and then, of course, must always test for this value, and also test for the normal value of the comparison. And we know in this specific case we don't really need that. So we must search for a better way to tell the compiler that we don't need it in this case. And so it means we should not map it to a value, but to a specific type. We do just use a different type for the AND. And then the compiler, whenever it sees B not equal AND, it knows AND is a different type than B and can switch to a more efficient version of that. So we just create a new type, which can be empty because it doesn't carry any state of interest for us. The null pointer also doesn't carry any information. And we can easily compare then our normal string character pointer to that specific value. Just looking then, having our special condition here, our string AND condition. But of course, our reduce doesn't work anymore because it expects two equal iterators of equal type. So we have to fix it, extend it, and introduce a new parameter, again a new parameter for the AND iterator. And now this generic code just triggers this comparison as in the sequential one, or in the non-generic version. Yeah? It's then bound to generate the equivalent code. So, and this still works for standard ranges which have same begin and end types. Works the same. Actually, this is it's proposed in the range-based algorithms proposal by Eric Niebler. It will also address that problem as far as I see. So you can look forward to have that perhaps in C++17 supported in a way. Okay, so we are done with this case. But now we have perhaps a more interesting case, which is sequences which have some more internal structure. So let's look at the simple benchmark. I have a vector of 100,000 floats and a deck of 100,000 floats, and I compute a sum or a reduce, it doesn't matter really here, of both. So what you think is the performance difference between these two cases? With high optimization, switch on. Who thinks there is no measurable difference? Sorry? Deck is faster. Vector is faster. By how much? 20% or 50%?
Depends on the cache.
Yeah, in this case I have chosen the value very small. The cache doesn't matter.
1-2%.
1-2%.
1-2%.
No, it's 100.
Yes.
No, 100 not. But for my computer, which is an old one, the thing is 4. On more modern, you could perhaps expect 8. The question is why this is. If you look into DAG, well, it's not really, of course, not a long array. It's a chunk or list of small fixed size arrays. So the data is not in a single segment, but in several segments. And such a data structure is called segmented or nested or hierarchical. Okay, So it's not only the DAG. If you compose, let's say, containers like that, vector of vector, you get a 2-level nesting. If you have a DAG of DAG, you get a 4-level nesting, and so on. Classical C-style pointers to arrays are also segmented. If you optimize code for multi-core NUMA architectures, you have perhaps padding to avoid false sharing. You have perhaps also artificial segmentation of an otherwise logical single sequence to have it local to your processor, and so on. So it's not so uncommon. And if you have these hierarchical data, there are 2 questions immediately. First, of course, how to iterate at all over such a thing in a sequential way. And then, as we see, there might be problems how to get this in a performing way. So first we take the first one, how to get a flat iterator over such a nested sequence. And then we'll look at how to exploit this structure to get an efficient implementation of our reduce. So first, a few definitions are in order because we will use that a couple of times. A segmented sequence or major sequence in our case, I will call the sequence of the segments. That is, in the case of the DAG, the sequence of the small fixed size arrays. So the value type is then a segment. And the segments themselves are, again, sequences, which I call here minor sequences. These themselves can be segmented again, like if a DAG of a DAG, then we will have several layers of that, or vector of vector, when the minor sequence is just a flat one. Okay, and out of these 2-level sequences, we can build, at least conceptually, a single sequence, which we call whole sequence or flattened sequence, which is just logically the concatenation of all the minor sequences. Okay, and this is the one we want to iterate over. So we have, well, according to our terminology, we have a major iterator, which is an iterator over the segments, and then a minor iterator, which is an iterator over the minor sequence or one segment only. So, and then we have also a flattening iterator, which iterates over the whole or the flattened sequence. And this is basically just a pair of a major and a minor iterator. It's rather straightforward. Yeah? And here's how we could, in pseudocode, implement such a flattening iterator. We have these 2 major and minor iterators. The increment works, okay, we have the minor iterator incremented by 1. If we're at the end of the current sequence, we have to increment the sequence and point then the minor iterator to the beginning of this sequence. Okay, the equality is also, in the simple case, in the general case, quite straightforward. We have first to compare the major iterators, and if they are equal, then also have to compare the minor iterators. I think technically it's undefined if we define just the minor iterators, because we can't define iterators from different sequences normally. It's not defined in general. Okay, and to get the value, we just look at the minor iterator, of course. Okay, there are some design decisions involved in if you want to write a generic one for all types of nested sequences. And one of the crucial ones is how do we want to represent the end iterator of the whole sequence. Again, the end iterator makes a problem. It's not really surprising. And there are different options here. So if we define with a large capital E the end of the major sequence, so it's past the end iterator of the segments, and PE is a previous one, which is the last valid segment. Sorry. Then we could choose a DAG approach and represent the end iterator by this last valid segment and some valid position within that valid segment. It doesn't work normally for typical combinations like vector of vector, because we can't guarantee we have some valid position to denote the actual end of the sequence. So the DAG does, if it's at the end of some of the last 3 segment, it just creates a new one. So there's only valid positions afterwards, so they can use. But this is an approach which requires support from the data structure, so we can't use it, for instance, for vector-vector. And here we could use something like that, the last valid segment and the end iterator of the last valid segment. That would work. But the drawback is you always have to be able to compute the last valid segment. And for forward iterator, if the major iterator is a forward iterator, let's say you have a singly linked list of vectors, you can't do that efficiently. So the most general approach is to just use the end iterator of the major sequence as marker and just forget about, in this case, of the minor iterator. Okay, there are, of course, drawbacks of that because all these things will get more complex if we choose the third option, and they are easiest for the first one because all is always valid. But nevertheless, in this talk, I will choose the third one because it's just the most general. And let's look how this changes our generic outline we have seen before. So first, of course, we have to store the end iterator of the major sequence. We have to define the iterator category. I will come back to that later because it's very interesting how this can be. And then we have also an additional test if we are at the end before we can assign the minor iterator to the new begin of the new segment. And also we have to think about how to actually access these begin and end of the major of the segments, which is not really, it depends on the concrete type. So it's different for, let's say, pointer arrays than for vector of vector. And the last thing where this affects our implementation is that also in the comparison we add an additional test here for the end iterator of the major sequence, because otherwise we can't have no meaningful full values here for the minor iterators. Okay, but basically it's similar to the pseudocode outline we have seen before. So first problem that occurred is how to access the minor sequences. So if we have something like composition of standard library containers, we can just use this syntax here, this std begin, std end. We are fine. If you have something like a seed style array of pointers, well, star m is the begin, and star m plus n would be the end, but we don't know the n because it can be different. It normally stored at some different locations. So we somehow need to pass this information also to our iterator, flattening iterator class. So again, extra parameter for that. So in this case, traits will not do it because we can't really map this type t star star doesn't have this information we need here for our, it doesn't give us the n, yeah, normally. Okay, I don't get further into that. Just keep in mind if you want to have a full working implementation of that flattening iterator, you need extra information to pass in via an extra parameter normally. Okay, then more interesting is the category of the flattening iterator of a major and a minor iterator. What can it be? What can it be at most? So if we have that example I cited before, a singly linked list of vectors, what could be the iterator category of that flattening iterator? Forward only, yeah. It can't be stronger, of course, than the weakest of both. Yeah, this is clear. Good, this is the easy part. And now let's look at something like that. It's both a random access. Can it be random access? Can it be random access? Let's look. So it means we have to be able to compute in constant time the advanced functionality, iterator plus n, the difference, and the comparison. Can we do that? Yeah? No? No, okay. You're right, we can't do that in general. So let's look. First, the advance. Well, the best you can do in general is if S is the number of sequences, you have it linear in the number of sequences because you don't know the size of the sequences. So you have to go through each sequence and then until you find your position. Exception is, like in DAG, you have fixed size sequences. Then you can do it in constant time. Yeah? Or if you maintain some clever pre-built information like a prefix sum of the sizes, then at least you can use some binary search to find the right segment, but still it's not constant. Yeah? It's logarithmic. So difference, same thing. Again, special cases, fixed sizes, or this prefix sum, then you can reduce it to constant time. And finally, the comparison, this can indeed be done in constant time because you just first compare the major and then the minor iterator. So yeah, in general, it's only bidirectional, even if both iterators are random access, except for the DEC case if you have fixed size segments, important special case. But some of that can be done in constant time, so the comparison, and the others can, of course, be faster than linear in the total size of the sequence. So there is an interesting mix of bidirectional and random access features somewhere in the middle. So I'm not aware of any algorithm that really benefits from that, but it would be worthwhile to keep that in mind if one has these structures, if there is perhaps some algorithms which could benefit from that. Like perhaps sort, it can benefit from. Anyway, let's see. Okay, but again, back to our original problem, which was that the same looking code was on the vector was 4 times faster than on our DEC. Now, this is our generic reduce again. And if we plug in our nice flattening iterator we just have defined, this expands to something like, oops, this one here. And this does look quite complicated. And the problem is similar as before. Of course, first we have some performance loss because of this extra logic of comparison, which is more heavy. But the real issue here is this doesn't make for the factor of 4, I think. What makes for the factor of 4 is, do you imagine what makes for a factor of 4 here? It doesn't vectorize. Huh? So normal generic code does vectorize, but this here doesn't, of course. Yeah. So what we really want if we have such a nested data structure is not a single loop, because how would you do it normally? If you nested loops, yeah, we want something like that, yeah. 2 loops, and then we have no problem, because the inner loop then is very simple again and can vectorize. So this example actually is a bit simplified. We will see later. But then we have our original iterators, and this can generate optimal code. So we must now think about, with our generic implementation, how can we achieve exactly that code we just have seen? Can we do that? And well, if you look at the iterator we have just defined, it somehow knows about the structure already because we have the minor and the major iterator, and somehow it has this knowledge. Just it doesn't give us the knowledge at the moment. Yeah? So we must somehow find a way to retrieve that information from the iterator to extract that 2-layer structure, and then of course use that to implement algorithm which is aware of that. And uses that structure to make this 2-level approach to these nested sequences. These nested loops. So it means we have to go from the flattening iterator to a structure-aware iterator, and this is also known as segmented iterator. I think Math also in his paper of 1998 has called it segmented iterator. But sometimes this what we have called flattening iterator is also called segmented iterator, which I think is a misnomer because our flattening iterator just presents the whole sequence as a flat one, but we want more. We want more. And if we think back about our nested loop code, we need a bit more from here. We need to access the types of the major and the minor iterators because we have to create instances of those. We must access the current major iterator. We must get bounds from major iterator, begin and end, for the major sequences to be able to, in the inner loop, to iterate over that. And we will also see in the general case, we also need to and major iterator and the current minor iterators. So how do we get there? Well, there could be two different options as usual. We could extend our flattening iterator type, our class, with additional functionality. This is what we will do. We could also try to do it with traits, which is non-invasive. We don't have to change the interface of existing iterators. Anyway, I think a flattening iterator must be a class. It can't just be a type def like in the flat case, like you can use a normal pointer as a iterator, but you can't use a pointer to pointer as a flattening iterator because it lacks information and functionality. So it does have to be a class anyway. And so it's only a small addition to our existing class anyway. So I opt for just extending the classes in this case. So and this is the extra functionality we need. It's not that much. Type defs, current major iterator, the end of the major sequence, and then we have to map any major iterator to begin and end. And also find the current position of our minor iterator in this sequence. And of course all the stuff we have seen before. Okay, and so I said the nested loops I have presented before. This was simplified code, and now here goes the full thing. First we have to reduce on a possibly incomplete first sequence because our minor iterator could be somewhere in the middle of the sequence, not at the beginning. Then we have a set of complete sequences which we have handled in our first attempt. And then also we have to reduce on the last part, which is also potentially a partial sequence only. And what we want to do is, of course, to have a same interface for flat and structure-aware iterator. So our reduce should be usable for both cases. That's because perhaps we don't know. I mean, it's passed to us and we don't know what is it structured or not. So we want to use the same algorithm, the same interface. So how can we do about that? Again, we look at the iterator and have a binary map. Either it's a structured one, a hierarchical one, or a flat one. And according to that map, we branch to a flat version or hierarchical version. And the hierarchical version again calls it this top level version because it could be a deck of double, and then we have not one level but 4 levels of hierarchy, and we want to exploit that recursively. So that if we have any nested level of sequences, we can go until the end and we have a nice flat loop at the bottom. So it will expand then in 4 nested loops in that case. So this is what we want to have. Okay, this is a basic logic. Here is a type map. I don't show the implementation, but it's straightforward. Just specialize it for hierarchical iterators. And if we have it's hierarchical, then we call the hierarchical version of reduce. And if it's a flat iterator, like vector of double, then we call the reduce flat. And our original reduce we have just renamed to reduce flat as a bottom case here. And now let's look at this code, and this will get now, because of these cases I just mentioned, will get a bit more complex. Here it is. And what we do is first we go over the first segment. We must always check if we are not yet at the end, then we are done. And otherwise we reduce over the first segment. And then we go do the middle segments, which are full. And at the end, we just do the last segment. I think it's easier to read that at home again, instead of trying to understand it here. This is more or less a similar code which is found in the original paper by Matt Austin. He has used a fill algorithm. The only thing I added is this additional comparison with the end of the sequence, because my iterator is more general and uses this end of the sequence as whole global end iterator. So it complicates it's a bit the implementation here, but it's then a bit more general as a reward. Okay, this is done now for our reduce. Now if you look, okay, now we look at the performance, yeah, if it really pays off. And here I have reduce with the benchmark before. I also added, just that you trust me, that with a vector we have optimal code, just something which normal C array is baseline, and this takes the same time. And this here is a chunk size I have used for the minor sequences. So all minor sequences contain 128 floats, which is actually the value used in the DAG. And then we see here we have this factor of 4, and if a vector float more or less has the same bad performance as a DAG if we use it with a flat reduction, and if we use it with a hierarchical one, we have a factor of 1.6, which is still not what we want. But this is a problem of the chunk size, so if we put it to some more reasonable value, actually we get the same performance here. So, seems to be more or less optimal code. Yes?
What about hierarchical for DAG? Where is this?
I don't have implemented the DAG iterator because it's not possible, actually, because you would have to use the internals of the DAG data structure. The DAG data structure doesn't expose, I mean, in the vector case, I have all levels exposed. In the DAG, I can't. I could, of course, take some GCC implementation and see what it, but I expect it to be the same, or even better, because it has fixed sized arrays, so it should even vectorize better, because you don't need any additional code then to, for the border cases in that case. So, but it would be an argument to add something like that to the DAG. Yeah. Okay, now that's fine, that's nice, but it works only for our accumulate. So, and this we have seen, this is quite a bit of code to do. Do we have to repeat that for all algorithms? That's not really attractive. So let's see if we can perhaps somehow abstract from the concrete algorithm, in this case reduce. Can we do that? So, well, let's first perhaps look at algorithms. So these are a couple of algorithms in the standard library. I think there are about 70 algorithms, and they add to them in each revision of the standard. Okay, here's our accumulate. We have already seen that COUNTIF can be implemented on top of accumulate. So this should be doable. Then we have, let's say, max element, which gives the iterator to the maximum element, is also kind of reduce. So should also work same. Well, the original paper was built based on fill. Well, it's not quite the same, but we'll see it's also similar enough that we can do that. Others like sort are, well, they somehow move things around the whole sequence, and this is not obvious how to do that. So the question is, can we somehow group algorithms into something which has same pattern? And yeah, let's try. It's the first try. It's not complete, not exhaustive, not really tested, but my first try would be, first we have these reduced type algorithms. Then we have, let's say, transform time, like fill for each transform, which turn out to be pseudo-reduces. So we can have same structure or same generic hierarchical version for them. I will show that. Well, then we have the find type, which are special because the find things return when they have found something. Yeah, they can return only. So this would need some different approach, obviously. And then we have the, let's say, I call perhaps swap type or permutation type, like sort, remove, rotate, or what you have, which just move things around in your whole sequence, and this is not so obvious. So I did not think enough about it, to be honest. I don't think that most will benefit from that. If they move things widely around, rotate, moves only a bit, that could perhaps benefit from a hierarchical implementation. I don't know. And maybe there are other categories. I don't know. Yeah?
5 minutes for the talk.
5 minutes for a talk, that's fine. I'm almost at the end. So we must distinguish also, I did not really look into these more complex cases. If we have more than one range input, it's more complicated because the ranges could have different segmentation property, and things get hairy if we really want to do that. Did not look into that. And if the predicates we have here in some involve subsequence like a JSON find or search, which uses a longer subsequence to match, but this is more complicated. I leave them out here. Let's look at the first two groups here. And we now try to find the common properties of these reduced type algorithms in order to make them fit in a generic hierarchical algorithm. pattern. First thing, observation is that while they don't have a common interface, we can somehow force them into a common interface by reordering of arguments and perhaps adding some dummy arguments. And the most important arguments are first the range, of course, begin and end, and this initial value, which some don't have and some have. And we compute that value dependent on the range and the init, plus some other arguments, which are, which vary. Okay, and the important property is that these algorithms can be composed. They are composable in some perhaps a similar sense than Bartosz mentioned before. So if we split the ranges into two, and we compute first the function on the whole range, we can also do it in hops. So first compute on the first range and use the result of that as the initial argument of the second call. Yeah, this is the composability, and this is the crucial property we need. So, of course, I said the interface can be adapted and has to be adapted because it not only doesn't really fit that order. So we would then perhaps, if you use to accumulate, we move the init to the begin. And if we have the count, if it doesn't have the init, we just create a wrapper which has this init, which is not very complicated. And even if we have these transform type algorithms like fill, we can wrap it into some wrapper which has a dummy argument. So here's an example for wrapper for the count if. So we just add this init argument here. It's quite straightforward. And now we can implement our generic hierarchical algorithm finally. So, and we branch the same way we branch for the reduce. Look at it if the iterator is flat or not, and then choose the right version. And well, we need a bit more algorithms, more arguments, of course. The R null and the R, the range. Of course, the algorithm F we want to adapt. So let's say this is the wrapper, wrap accumulate, wrap count if, for instance. And finally, all the other arguments this particular algorithm has. And if we think about, or if we hear the term any number of additional arguments, maybe in C++11, a bell should ring in your head. We use for that these variadic templates to match any number of additional arguments. So basically, this is the same structure as you have seen before. We have only additional arguments, algorithms, then our core arguments, and then any other arguments, which are just passed to the actual algorithm. So in the flat case, we just call our flat algorithm, and we are done. And in the hierarchical case, we just have a hierarchical implementation, which is very similar to what we have seen before. I didn't repeat it here, which is quite straightforward how to do that now. Once we have defined this common pattern or this common protocol for our algorithm. Okay, and here's an implementation how to use it for count. So if we have this hierarchical count, we pass it the wrapped count if of a standard, pass it appropriate initial argument, and all the other parameters here. And accumulate would also be simple then. Okay, yeah, and I think this approach would permit to wrap most of the interesting algorithms. I think most of the others won't really benefit from the approach, but some which do numerical computation could benefit from that approach. So, as I said, because for these there is the potential gain is very high because of the vectorization, which is blocked by the normal flat iterator approach. Okay, and well, there is certainly some more work to do. The classification is far from complete, and if we do that, we will find hints for improving interfaces. For instance, when I looked at the copy, which takes two ranges, I found that to be composable, the copy should not just return the input iterator, but also the output iterator as a pair. Then we could really compose those, both of them. I think a similar strategy could be applicable. The strategy of building groups of algorithm could also be applicable to have generic parallelization of some classes of algorithms, but this is certainly a different talk for now. And now, not to say and again, spasiba.
Вопросы?
Seems I answered all questions already. Ah, there.
Thank you very much for your talk. It's very interesting revising of the ideas of iterators. And I have a question. Where do you find the most applicable your approach in some projects? Where do we find it?
This is new code I didn't use in projects, but I often have nested data structures where I would then likely have resorted to manually boil down it to a loop. And I could imagine I would use that at some places where I have a reduce over or something similar over a nested structure. I think it could directly benefit from people who often use DAG and call standard algorithms on that if the DAG had a hierarchical version of the iterator, because as I've shown, the benefits could be quite dramatic.
Where could be the most benefit from this approach?
I think the most benefit is for people who use nested data structures and often call generic algorithms or can't call them at the moment because they don't perform.
Some kind of early bailout mechanism so that the reduce-based algorithms can also provide for find-based algorithms?
Yeah, I can think about it. I haven't implemented that, but I think it's not so difficult to adapt the code. If we go back to the code, it should not be so difficult to let's see. Here. So, well, you would add perhaps some additional flag to the interface, which tells us if it finds something or not. Find, for instance, gets back the end iterator if it doesn't find something, and others do something else. We must also have a common interface for that. So I suggestion would be just to have a pair of the normal result and the bool, and the bool tells us if it found something, and if we can just return here at that point or in the next loops or so. So I think it's doable, definitely.
Now a question.
Can we please move this conversation in a more individual order? We should prepare a room and presentation.
So what, we need to go or we can continue? Okay, thank you.